Good afternoon, everyone. I am Dr. Jason Kim. I would like to present about risk and safety management system in tunneling, especially focus on urban tunneling project. I introduce myself. I studied in Seoul National University in 1993. After graduation, I worked Daewoo, Sambo, and Samsung Construction Company. After that, I studied University of New South Wales in Australia, and I worked in the Parsons Brinkhoff in Singapore. Nowadays, I worked in Ghana Engineering Company in Korea. I also activated in academic and society and authority, and including the General Council member of Korean Society for the Lock Mechanics (KSRM) and the General Council member of the Korean Tunneling Association (KTA), and published some books about geological and lock engineering and the theory and practice in tunneling. My topic is included the 5 contents. The first is the risk management in tunneling, based on the tunnel risk management guideline by ITA. The second is the safety management system in tunneling, based on total safety management system. The third is the case review of tunnel collapse accidents in UK, Singapore, Taiwan, and Japan. And the fourth is the risk management practice in tunneling, and cable tunnel project in Singapore, and GTXA tunnel project in Korea. Lastly, the key issue in mega tunnel project, Singapore, Hong Kong, Sydney, Tokyo, and London. The first is the risk management in tunneling. There are so many actual risks in tunneling: unexpected ground condition, collapse up to ground surface, and the damage due to ground settlement. This is some example of the actual risk in tunneling. Sinkhole, the Cairo Metro Tunnel in 2008-9, and the surface collapse Quillen Metro line. The sinkhole, the Brightwater Tunnel, Washington, the surface collapse in the Hangzhou Metro 2008. Also, some actual risk in tunneling: surface collapse, the Singapore MRT 2004, surface collapse in the Shanghai Metro 2003, and the surface collapse in the Munich Metro in 1994. There are actual risk related to the log engineering. Log burst in the Gotthard-based tunnels, and collapse and the failure of the face the tunnels, and the ground collapse and the jury tunnels, and severe convergence and squeezing in Gotthard-based tunnel. You can see the collapse of the tunnel in the Heathrow Express link in UK in 1994. The tunnel collapse occurred in the night of October 21st in 1994. The tunnel collapse is very, very serious. There are so many making some tunnel collapse cause. The second is the face failure in Ottawa or LRT excavation in Canada in 2016. There are no injuries and there was no damage to surface structure, but it was a significant sinkhole that opened up above the LRT tunneling works in the downtown Ottawa. The other example, tunnel drive collapse in Germany in 2017. The collapse of the TBM tunnel drive in association with ground freezing support under the line Valley Flight and the passenger railway line in the Razat in Germany has halted all rail traffic between the Karlsruhe and Basel. And the tunnel failure in the Fukuoka LRT in Japan, 2016. The load cabin accident caused by tunneling is described, and the possible mechanism of the failure is analyzed. The cabin is measured about 30 meter and 27 meter in length and about 15 meter in depth. This table describes the tunnel accident from the 1994 to the 2004 based on the ITA. There are so many the tunnel collapse in all around area. This is some excavation sensitivity the factors based on tunnel incident. So many the excavation method, conventional, manual, natural blasting. The sensitive factors: earthquake, flood at space, fire, explosion, like this. This is a geological risk in tunneling, especially the geological hazard and risk in TBM. There are many hazards about ground collapse at shield tail, ground pressure to the shield, ground excavation without TBM movement, and the weak soil formation, mixed space guiding control of tunnel, high water pressure, swelling in pressure, stroking, clamping of TBM, face collapsed by groundwater inflow, gas detection. This is a geological hazard and risk in TBM continuously. The overstressed lining by groundwater pressure, and the excavation material or the transportable through the conveyor belt, exceptional high wearing of the excavation tools, and boulder within soil formation, natural caverns, and approaching the fault zone, the water inflow through the segment, contaminated ground, and the treatment of the excavation material, the thermal impact. This is about geotechnical risk, and they divide two: on the surface and on the ground. On the surface, the settlement of building and existing structure, the settlement of the surface utility, and the vibration. The geotechnical risk on the ground, including the deformation, instability of the crown and of face, and the cave-in, and the rockfall and the wedges. This is the GBR, Geotechnical Baseline Report. Geotechnical baseline is to be established for all anticipated conditions. GBR has to establish some realistic basis for all contractors preparing B, and for the to form the base of the evaluation contractor claim for the differing site condition. GBR shall help in preparing risk register on specified baseline for the possible risk. GBR is the basis for the equitable contractor risk sharing and the risk allocation between the project owner and the contractor. GBR issues estimate about the distribution of different material along the alignment, and the different property of the intact material, property of the ground mass behavior, groundwater condition expected, and construction impact on the adjacent facility, other geotechnical and the man-made source of the potential difficulties. And in 2002, the HSE report in UK lesson from the incident. Hazards were not identified by all the parties, and risk were not controlled during the construction through the defensive system. Widespread organization failure, design, quality control, engineering, supervising, and safety management. That's why we have to carry out the explicit risk management and the better communication between client, design, and contractor. A lesson from the incident. The first is the robust, fully engineered design. This is including semi-empirical design, use of the past experience in similar condition, observation of the actual ground condition, and experienced site staff, and the numerical approach, and the detailed characterization of the ground by investigation, sophisticated numerical modeling by the well understood for the ground condition, explicit proof by the calculation of design. The second is tightly controlled risk management. It's including integration of the preventive system, the qualified staff on site and decision making, and independent checking engineer to verify. This is the engineering design process proposed by BTS, British Tunneling Society, 2004. This is a normal design process: conceptual, the detailed design, construction, and like post-construction. They also have to check the risk management and the hazard identification and the risk assessment and the risk management. This is guideline for the tunneling risk management proposed by ITA 2004. A risk equal function of the hazard defined by its consequence, severity, and the likelihood of occurrence. Risk assessment: identify risk source, identify risk cause, identify consequence, identify the likelihood or the probability, identify severity, and finally ranked risks. This is the risk management of tunnel works proposed by ITIZ, International Tunneling Insurance Group, 2006. It is published by a code of practice for the risk management of tunnel works, including some contents, object of scope, the compliance of code, introduction, risk assessment and management, and client role and responsibility, like this. This is a project management based on the risk-based design process. As shown these figures, is risk identification, risk analysis and assessment, risk ownership, risk mitigation and contingency planning, and the risk monitoring and control and the audit process. This is a risk management process. Risk management process is not only single event or continuous processing during the entire project. The risk control is a part of the project life cycle from project initiation to project completion. Risk register: risks are to be managed to ensure their reduction to level as low as reasonably practical, a lot. Risk assessment are to be recorded and summarized in the risk register at each stage of the project. Risk assessment means identification of the party responsible for control and management of the identified risk. Risk management is a systematic process of identifying risk, qualifying risk, identifying the action to eliminate and mitigate risk, and identifying the method for the control of risk and allocation risk to various contractor parties. Risk score equal probability P the cost, and the risk impact RI. In other words, frequency or likelihood of occurrence, and by consequence and severity. This is some example of the probability and the risk impact. This is the consequence analysis proposed ITA 2004. Classification of consequence and divide 5 class: disaster, severe, serious, considerable, insignificant. Depending on the injury to the third parties, damage to third parties, harm to environment, and possible delay, minimum, or others. This is a frequency analysis proposed ITA 2004. Frequency of event in the construction period. They classified the frequency class 5 class: very likely, occasionally, occasion, unlikely, very unlikely, like this. This is acceptability criteria proposed ITA 2004. They divide for the criteria: unacceptable, unwanted, and unacceptable and negligible. Acceptable is risk shall be reduced at risk to unwanted, regardless of the cost of the mitigation. Unwanted, risk mitigation measures shall be identified. The measures shall be implemented as long as the cost of the measures are not disproportionate with the risk reduction obtained a la principle. Acceptable, the risk shall be managed throughout the project. Consideration of risk mitigation is not required. Negligible, no further consideration of risk is needed. This is the risk matrix proposed by ITA 2004, risk acceptance matrix. As I mentioned, consequence class: disaster, severe, serious, considerable, insignificant, and the frequency class is very likely, occasional, unlikely, very unlikely. The 5 by 5, total 25 the risk item, and divided by 4 groups: unacceptable, unwanted, acceptable, and negligible. This is the risk management process. First, the planning and policy, the system definition, hazard identification, and frequency analysis, and consequence analysis. They also classify the risk, and based on the risk acceptance criteria, and finally risk evaluation. If the unacceptable risk reduction measures to have to carry out, and the risk if the acceptable, the risk management is finished. Risk mitigation. Risk as a combination of the probability and the impact, and the focus on from the initial risk to the residual risk through the mitigation. This is some example of the risk mitigation: choice of the different alignment, and the choice of structure with less susceptibility, and so choice of structure that is able to suffer local damage without total failure, like this. This is an example of risk matrix: before and after measure. Before the risk disposition, we have so many take the measures to reduce some risk to the low level risk. As summary and the keywords: the uncertainty and the georisk in underground tunnel. Geo uncertainty is always present in underground tunnel construction. Tunnel construction has large geo risk due to geo uncertainty. And second is the risk analysis and assessment in tunneling. In tunnel construction, risk assessment method has been established. Especially the quantitative risk evaluation method were presented by ITA and ITIZ. In risk management in tunnel risk management system has been required and mandatory, and the risk management system shall be applied from design stage to the construction stage. The second topic is the safety management system in tunneling. A principle in safety in design. Principle 1. The persons in person control. Persons who make the decision affecting the design, product, facility, or the process are able to promote health and safety at the source. Principle 2. The product life cycle. Safe design applies to every stage in the life cycle, from the conception through to the demolition. Principle 3. The systematic risk management. The application of hazard identification, risk assessment, and the risk control process to achieve safe design. Principle 4. Safe design acknowledgement and capability should be either demonstrated or acquired by persons with control over design and design. Principle 5. And information transfer is effective communication and documentation of design and risk control information. Design for the safety in Singapore. LTA implemented a safety management system encompassing construction safety, rail system safety, and road system safety. PSR required safety submission at the following 3 stages: preliminary design, detailed design, and post-construction. The figure shows the guideline on the design for safety in building and structure in Singapore. Design for safety in building and structure in DFS. Considering safety in the design phase, be it concept design, detailed design, and even pre-construction design, making decision in design to mitigate or minimize the risk to those performing the works downstreaming. This is a DFS guide process, and from the site risk register, concept design, detailed design, tender stage, construction stage, maintenance stage. We appointed the coordinator, design for safety coordinator, always the associated with the risk register and risk assessment. Design for construction safety, DFCS in USA. This is some established design for the safety expectation, and including the construction and operation perspective. Identify design for safety process and tools. The process of the considering the construction site safety and health in design of the project. Designing for the safety constructability. This is prevention through design, PTD. Prevention through design equal design for safety or safety by design. PDD in construction is explicitly considering the construction safety in the design of the project. PTD design review and process, including the hazard identification, risk assessment, and the design option identification and section. This is the PDD process, showing the hierarchy of control of risk. This is the safety management in USA, the Safety Management System, SMS. The safety culture of the organization and includes senior leadership commitment in frontline engagement and management accountability and continual safety process improvement derived from the data-driven safety risk assessment. This figure shows the 7-step risk management process. This is the designing for safety in construction by EFCA, including risk assessment, matrix method, hazard material, design team, realistic limitation, and recording the decision and information for the contractor. Designers the assessment of safety during the construction and maintenance taking accounting for the principle of the prevention. This is the design for the safety in UK. Safety by design based on CDM, construction design the management. The safety by design is concept and movement that encourage construction to design out health and safety risk during design development. Safety is determined during the safety design, and we also the CDM coordinator, principal designer, and like this. This is the safety management system proposed by HSE. Safety management system for the construction is a systematic way of identifying hazard and managing risk relating to the construction workplace. SM will typically including identifying all safety hazards and the risk management procedure and the continual monitoring and the continual improving of the effectiveness of safety and the management system. These items are managed in the Plan, Do, Track, Act cycle of the continual improvement or the PDCA cycle for short. This is a historical the tunnel collapse accident in Nicol Highway collapse in Singapore, 2004. Through the based on the investigation, we lesson learn 18 items. The first, improper design, improper analysis, and the drill mode boring, appropriate back analysis, construction control, unproven method. Measurement must be taken according to the schedule. Instrumentation problem. Data must be proposed properly, and enough manpower. The use rate of the increase. The site engineer, contingency plan, the excavation analysis problem, observational method, qualified geotechnical consultant is needed, and the reasonable construction period, like this. Through the investigation, they recommend some system design. Don't be overconfident about analysis, and use appropriate soil parameter in adopt correct method. After that, accredited site investigation in GIBR and adopt the independent design checking system and complicated design submission process. In construction stage, should be checked and prepared for the risk and safety. Implement of observational method in diligent and independent instrument and qualified engineer on site, a site and risk management system PSR process, and strict design change submission procedure like this. This is a building control system in Singapore. In these figures, and the designer checker and the supervisor, always cross-checking all the design and construction the problem. This is the flow chart of the U underground building works in Singapore. In this flow chart, QPS, QPD, AC, QPS Geo, QPD Geo, AC Geo, all party cross-checking the all issues in construction problem. This is the total safety management system, the safety policy, management committee, and the management process. In system, including the project safety review, PSR process, safe to build, safe to use, and also the PSR review, commit and subcommit. Total safety management system is identify major risks and address them, reduce risk at source, and protect the safety and health of the problem, people involved in construction, operation and maintenance, and the general public. The review of risk by independent parties. Also the process, including the PSR process. PSR process is a systematic and effective risk management approach to manage major hazard from the as early as feasibility stage right through the concept, design, and construction and maintenance phase of the project. Hazards are identified and addressed through this process. PSR committee comprise experienced members of the different background. This is the PSSR process, and through the project life cycle, feasibility, concept design, construction, handover, operation, all stages have to submitted self-submission, including the major risk identified and eliminated. Residual risks are mitigated and controlled at downstream. This is the PSR process pre-construction stage, and identify and follow up major risks along the alignment of rail and major road project risk due to associated with. This is the PSR process, the construction stage. Ensure the contractor demonstrate a competent understanding of the project hazard prior to the commencement of the works. This is the PSSR process handover stage. Provide information and maintenance hazard and operational safety manual to the operator. This is a PSR commit, and including some PSR submission process. This is the CDSS report, Civil Design Safety Submission report, including the detailed design and groundwater drawdown and settlement analysis, and the damage assessment, induced tunneling, and instrumentation and monitoring plan, and finally risk assessment, including the hazard identification and risk ratio and risk mitigation and control measures. This is the CNSS report, Civil Construction Safety Submission report, including the detailed construction plan and the communication and the management of the work, and the hazard identification and the risk management, and finally environmental control plan. This is the risk management strategy. As shown these figures, risk identification, risk evaluation, and risk treatment, and risk monitoring, and finally risk closure. The final goal is zero extent. The summary and the key words in second topic. The design for safety and construction safety. Design for safety, DFS, is safety's constructability and prevention through the design review and process. And the safety management in system in tunneling, PSR, process is required in Singapore. Building control system in Singapore has been established. And safety management in tunneling, a safety management system has been required and mandatory. A safety management system shall be applied from the design stage to the construction stage. The third topic is the tunnel collapse extent. The first is the Heathrow Express tunnel collapse in UK. The tunnel collapse in early hours of the Friday, 21st October 1994, and continued to all fail over the number of the days. The failure brought the chaos to the heart of the Heathrow Airport. Fortunately, no one was killed or injured in accident. On the third day, the ground stabilized, but the incident has created the dramatic crater in the airport between the both runway. The sunken ground affected the car park and caused the nearby building to crumble too. The tunnel crossover and the station for the various terminals were constructed during the sprayed concrete lining, SCL, previously known as the New Austrian Tunneling Method, NATM. From the Heathrow Express tunnel collapse, we earned lesson learned. First, lack of the awareness of risk and self-certification of qualify following a competitive tender, separation of the permanent and temporary work design, separation of the compensation, grouting, and tunneling monitoring process, and lack of the appreciation of difference between hard rock and soft clay behavior. Design not considered sufficiently robust, joint buildability poor. The flattened invert made construction tolerance more critical. The profile difficult to check because no lattice girder. Monitoring regime unsatisfactory. Ground condition as unexpected. The method of tunnel construction is the SCL, the tunnel cross-section, joint details, and the flat invert. NATM can give excellent result in general. Failure likely to arise from the multiple causes. Design need to consider ease of construction. CDM monitoring should be continuous, auto-processed, and web available. Supervision must inform all design objectives. Need for the integration and communication of the team. The second accident is the Nicol Highway MR tunnel collapse in Singapore. The Nicol Highway collapse was a construction accident that occurred at approximately 30 p.m. Singapore time. When a tunnel being constructed for the use by MR train collapsed. The incident was caused by the collapse of tunnel retaining wall, creating a hole 100 meters long, 130 meters wide, and 30 meters deep. The collapse of the highway led to the damage of the gas service line, leading to the explosion and subsequent fire. Supply was shut off for the demand pipe. This is the collapse site M3 area. This figure shows a failure mechanism and some the retaining wall and bending and some collapsed. This is also the show the failure mechanism, the retaining wall, like always the collapse in the soft clay area. This is the failure mechanism, totally collapse the retaining wall and the ground level and the substance and the explosion of some load. The third is the Kaohsiung MRT tunnel collapse in Taiwan. In August 2004, a section of the subway tunnel at the west end of the Orange Line collapsed during the construction due to loose sand underground and water brick incident. Four low-rise buildings near the collapsed tunnel has to be evacuated and later on had to be torn down due to major structural damage. This is the area of the Kaohsiung MRT tunnel collapse in Taiwan. This is some MRT line, this collapse area. It was noticed that outburst of water occurred while excavating too near the bottom of the sump pit, and authority immediately respond to the water ingress event by the dumping sand back and quick set cement, but in vain. This is the TBM tunnel, two-lane tunnel, and across this is a cross passage. This is some position of the collapse from the leakage, the water leakage. The two 830 meter long, 2.1 meter wide parallel tunnels LUO 9 were excavated during the shield tunneling method. 6.24 meter diameter early earth pressure balance EPB shield was responsible for the tunnel boring operation. The end were linked to the station 07 or 08 of the Kaohsiung metro system, and across the passage with a middle sump pit at 32.6 meter depth was built for the safety purpose. This is the cross passage 1, 2, 3. This is the failure mechanism. The scenario for the progressing the leak extent. First is the some leak in the sump, like this. Some the piping this area. The second is the shorted path for the ground of the seepage in this area to the sump. The water ingress, water leakage path beneath of the sump. The third is the formation of the surface cave in the south side, and some propagation to the surface area, and finally a collapse and the load and on the pathway structure. This is the longitudinal profile for the failure mechanism. This area, this is the cross passage. This is the piping in the soft ground. This is the propagation to the surface, and formation of some cave in the south side. This is the formation of surface cave in and north side. Totally the collapse and the north side and south side connected to the tunnel area. This is the Fukuoka subway tunnel collapse and sinkhole in Japan. The cave in front of the JR Hakata station in Hakata Road and Fukuoka, also the cause of power blackout at railway station and other facility, and seriously affected the communication and the network. The municipal government is supposed to fill in the sinkhole up to the level of groundwater that has flowed into the pit, or about 3 meters below the street level by the evening of the November 9. We can some video about the Fukuoka subway tunnel collapse. This is some video showing some local collapse. This is showing the sinkhole. Some the cables, the pole is pulled down into the sinkhole. Some structure is falling down. After that, the sinkhole is more enlarged. The other side is collapsed instantly. After that, very shortly the collapse is the propagate like this. And see the in the night we can see the largest sinkhole on the road. In the early in the morning, they like this. Finally, the sinkhole is collapsed like this. After the big sinkhole, and the tunnel is totally collapsed like this. This is the plan and the longitudinal view of the accident area. All this section, the construction method adopted was a new Austrian tunneling method, NATM. All the ground fasten method was used as a pre-support measures. In Japan tunneling, the main tunnel used the shield tunneling, especially this area applied to the NATM method. This slide shows the shape of the collapse and the sinkhole. It appears that the water level in cave was at the depth of about 5 meters. The depth of the water level was more than the height of the one story of the adjacent building from the ground surface. This is the tunnel area. This is some sinkhole. This is the connected total. The collapse the volume is 2,200 cubic meters. This is the weather zone where the accident occurred. The design tunnel was a cross section close to the ellipse, and with a maximum width of the 15.77 meters and the height of the 11.50 meters. This is the connecting this area, the soft soil. This is some weathered soil. This is some crown of tunnel connected in this area, and including the associated with some leakage of the underground water into the tunnel. This is this figure shows some mechanism of some collapse mechanism. The estimated thickness of the shale layer above the crown of the tunnel was approximately 2 meters. It reveals that the top elevation of the shale layer was deeper than the initially estimated value. The meaning is this is the differing siting condition between the estimated in design stage and the actual ground condition in construct stage. The very shallow depths of the shale layer inducing some water ingress into the tunnel, and finally induce totally the collapse of the tunnel, and occurred the sinkhole, road sinkhole, like this. This is the sinkhole at the Tokyo Ring Road Tunnel in Japan. The sinkhole was found at ground surface in the residual area in Tokyo in October 2020. The site was above the construction line of Osprey's balance shield tunnel within 16.1 meter in diameter, and the crown at the depth of ground level minus 47 meters. A sinkhole was reported by Eastern Nippon Express Company. It was reported the location was above the tunneling site of the Tokyo Outer Ring Road main line tunnel. The size of the depression was 5 meters by the 2.5 on the ground surface, like this. The shield was passed below the sinkhole. Sink point was about 40 meters below the surface on September 14, 2020, about 1 month earlier than the sinkhole appears. Based on the laser scanning and the seismic survey along the shield line, additional void zones were identified. This slide shows the concept of the deep tunnel in Japan. In Japan, and below the 40 meter the ground surface, they call it deep tunnel, deep underground. They helping some developing the urban underground space like this. The relationship with the shield tunnel construction on the Tokyo Outer Ring Road is unknown, but just in case the shield tunnel construction on the Tokyo Outer Ring is once. Sinkhole occurred in the 3 places. It directly relates to the tunnel construction, the upper section of the TBM tunnel. This is the first the occurrence, the second, the third. Total 3 places, the sinkhole is observed. The cause of collapse, the ground relaxation due to the inflow of soil when work is resumed. And sinkhole due to the extended ground relaxation due to over excavation. This is explain the failure mechanism. The first is the shield tunnel, and the second is the relaxation of the ground. The loosening is often occurred. The third is the opening on the ground is the making after finally the connecting the surface, ground surface, and the collapse, and the sinkhole is occurred like this. The summary and the key were: the first, accident case of the tunnel construction in overseas cities, large scale collapse accident in UK, Singapore, Taiwan, etc. The safety problem and issues very, very serious in modern tunneling. The type of accident by tunneling method in urban area. First is NATM, the construction management considering ground characteristics. The TBM, tunnel boring machine, and risk management in the construction is required all stages. The analysis of the accident case in tunnel construction. The problem of the ground substance sinkhole due to tunnel excavation is occurred. The tunnel collapse mechanism in deep tunneling is have to analyzed by checking some risk problem. The process of risk management practice in tunneling. The first is the transmission cable tunnel project. This project, this is figure shows some map of Singapore. This is the line of the north, south, and east, west. Total NS1, NS2, NS3, EW1, 2, 3. This is the some shows us a transmission cable tunnel in underground. This is a cable tunnel project located in the ground level minus 60 meters. The transmission cable tunnels and the client the Singapore Power Asset. The transmission cable tunnel project 2 billion and the long-term solution designed for the facilitate transfer more efficient maintenance and replacement of existing and future cables. The construction combined by included two tunnels, one running north-south and another east-west. Total 35 kilometers in length, built to 60 meters underground. Commenced in 2013. This is the north-south transmission cable tunnel contract NS2. I worked in this project in Singapore. The consultant passes being called. This slide shows the alignment of the this NS2 project. As shown these figures, the main three shafts like this: Mandai shaft, Tagore shaft, and Amokyo shaft. This is a layout of tunnels. First of all, the excavated shaft using the NATM or the SCL and excavate edit tunnel and making the enlargement tunnel. Finally, the excavate the cable tunnel by TBM method. This is the design and construction NS2. This total length is 5.38 kilometers, and the combined the board tunnel and the shaft and the mine tunnel building and the mechanical and the electrical works. This is the construction process using the Mandai shaft, Tagore shaft, and Amok shaft using the TBM machine 1 and 2. This is the detailed information about the shaft. This is the construction sequence, and first is the making the shaft using the NATM method. After that, making the some Tagore shaft and enlargement tunnel for the preparing to the TBM the excavation. After that, launching the TBM machine and excavate to TBM 1 and 2 and about 5 kilometers using TBM machine 1 and 2. And the third two is the lining and lining under the shaft and making the some the electrical and the architectural the facility in each the shaft. In Singapore, the risk management system is mandatory, especially the provide for by the guideline of risk assessment. This is the provided by SPPA, Singapore Power Asset. The first is the frequency of occurrence, like rating the poor rating, and frequent, probable, occasional, remote, like this. This is the accident severity classification, as shown this in this table, and the rating 1, 2, 3, 4, and the catastrophic, and the critical, and the marginal, and the negligible, like this. This is the risk index matrix and risk acceptance criteria. The severity category 4, accident frequency category 4, and the total 4 by 4, 6 the risk item. It's divided by A is the intolerable, B is the undesirable, C is tolerable, D is acceptable, like this. This is example risk register for the TBM driver in NS2 project in Singapore. This is some risk ID, hazard codes, some risk assessment, initial risk assessment. After that, risk after some the measure residual risk assessment result. This is the risk identification for the TBM drive, and the risk register 1 from 1 and to the 11. Total 11 risk register is the identified. This is the identification for the TBM driver. Each risk ID for the we do also the take the mitigation and future action like this. Future action is the probe drilling, additional site investigation, and ground grouting and quality control like this. This is some risk and mitigation measures. Risk identify risk. The risk is the tunnel face instability. The engineer also have take mitigation measures, checking the carefully the monitoring data, experienced and competent TBM engineer, and the designer specify the phase pressure, designer specify impact and damage assessment, and the probe to be carried out, and the review team including like this. This is in the risk index mitigation. Before the mitigation, total 11 risk ID identification, and A is the 7. Also the A is the totally the 11A the class. But after mitigation, we reduce the risk level to the B class. This is another the risk management practice in tunneling. GTXA railway tunnel project in Korea. I worked involving as the consulting engineer in this project. GTXA representative urban metropolitan intercity tunnel mega project in Korea. Safety and civil compliance became an issue as they passed through the urban area underground tunnel. They require the reasonable safety management and quantitative risk management. This is the total flame view, the alignment of the tunnel GTX railway tunnel project. This project is to divide the total 6 location. I worked in the practice review of the risk management at this area, the 3 section. This in this project, risk index metrics and risk assessment criteria based on the ITA frequency, the classification 5 ranking, the consequence classification, also the 5 ranking, the unlikely, likely, occasional, unlikely, very unlikely. Consequence classification: disaster, severe, serious, considerable, insignificant. This is a risk index matrix and risk assessment criteria based on the ITA. This is some total 5 the risk matrix and divide 4 group: the unacceptable A, unwanted B, acceptable C, negligible D, like this. First of all, the risk category for the deep urban tunneling. Derive the detailed evaluation item by process and the risk item. By construction process, tunnel, vertical, tunnel, temporary wall, shaft, structure. Risk category by induced hazard, geology, ground settlement, groundwater, blasting, structural damage. The left side this category 4, right side is category 5. Total 20 groups of risk are derived and evaluated. This is the risk evaluation sheet, including the risk ID, design check, work activity, hazard cause, impact, initial risk category RI, mitigation measures, residual risk category RR, future action, risk owner, action owner, due date, risk exposure period, target risk sharing, status, key station, remark. Assess all risk rating for all risk factors and specify the management risk measures. This is the result of the risk evaluation, showing that the sheet. This is the each risk ID, the analysis, the initial risk and the residual risk, and like this. This is this risk analysis and evaluation is the quantitative effect of the key risk reduction in this project. Before the risk, before the mitigation risk, the index matrix, and after mitigation risk index matrix, we all engineer compare to the some the people and after taking the lowest risk the mitigation. People and after risk mitigation for deep urban tunneling in the GTX-A project. Total 174 risk and established countermeasure. And the people the mitigation A class 8, B class 99, C class 67, D class 1 is the after mitigation the all the A class, B class risk is reduced to C class and D class. The after the through the mitigation. Risk index matrix is evaluated before and after risk reduction measures. This is a key risk in main tunnel section. This is a plane view. This is a longitudinal view. We can check the key risk area. This area, this area, this area, this area, like this, based on the risk analysis evaluation and risk management system. This is the total sum of the risk and divided by the category tunnel, the retaining wall, temporary wall, and the shaft, and the station. As shown in this table, in tunnel the category total some the risk item is divided A, B, C, D like this. In tunnel the category A class risk is 3. This is the risk counted by the risk category: geology, ground settlement, groundwater, blasting, structural damage. In the relate to the geology, in the total risk count is the 61. A class 3, B class 26, like this. This is summary of the detailed risk assessment. we can see the quantitative risk item, risk ID in this project about the tunnel or the tunnel geology, tunnel ground settlement, tunnel the groundwater, tunnel structural damage, tunnel and in blasting, like this. This is also the can see the some summary of the detailed risk management. Shaft relate to the geology, shaft relate to the ground settlement, shaft relate to the groundwater, shaft relate to the structural damage, shaft relate to the blasting, like this. The summary of the key words. The case of the risk management cable tunnel project NS2 in Singapore. Establishment of the risk management standard by project characteristics for each client. The strict apply PSR process by process step and require for the construction approval. The case of risk management GTEX-A, establishment of risk assessment criteria by the characteristics of urban tunnels. Classifying the risk by key process risk item and establishing key risk measures. Risk safety management in urban tunnels. Risk management due to uncertainty is required due to nature of tunnel characteristics. The quantitative risk item, the derivation and continuous risk management plan is compulsory required. The topic is the key issues in mega project. The first is the cable tunnel project. As mentioned in this topic, this project is a big project in Singapore in urban tunneling. In this project, we can see some special advanced system. The first one is IDMS, Integrated Data Management System, to facilitate to real-time access and monitoring of the instrumentation data from both the owners and contracts. This is some geosystem suited for the incorporating into the corporate BIM. Second is the BIM application. In Singapore, BIM e-submission is the mandatory. This is some example of Singapore BIM core, and all BIM models alignment must be geo-referenced for the federated system integration. This is the example of the BIM application in cable tunnel project. The 3D overall view, 3D general view showing the cable route. This is the total safety management system. As I mentioned in the previous section, safety are assured through the project safety review (PSR) process. PSR provide for the formal and structured assessment of the safe to use and aspect to LTA project from the beginning of their life cycle. The other is the Integrated Digital Delivery (IDD) in Singapore. IDD refer to the use of digital technology to integrate work process and connect stakeholders working on the same project throughout the construction and the building life cycle. IDD is one of the key thrusts in the construction industry transformation map (ITM) and is aligned into the nation's effort to transforming in construction industry by creating a highly skilled workforce training in use of the latest architecture, engineering, construction, operation technology. The next project is the West Connects Underway project in Sydney. This project is a mega project making the underway in urban area. About 30 km in length, West Connects comprise the widening and extending underground of the M4 and the duplicating of the M5 and connecting the two underway underground motorway. This is the tunneling method in urban area. Tunneling equipment today, all the major road tunnel in Sydney have been constructed using road header rather than TBMs. There are several reasons for this clothing, including the variable cross section. The second is the sandstone is particularly well suited to the use of the road header, and a lot of the road tunnel constructed to date in Sydney are undrained. The third is the very short overall tunneling program can be achieved by employing the multiple machine at a number of the headings. This is the interactive the map area for the West Connects project. We can see all the people can see the status of the construction and some depths of the tunnel like this. All information are provided to the people. This is the urban tunneling is issued, but in the West Connects underway project, tunneling are deeper than 30 meters. Can reduce the risk and the substance, or the reduce and the noise and vibration during the construction. This is the community information center in for the West Connects underway project. The center provides modern and comfortable space for the visitor to meet with the community engagement team and ask questions and learn about the progress underground tunneling works. This is the 4D beam application. In Sydney, in Australia, the beam application is mandatory, all projects. 4D means the relate to the time base, the schedule, managed to the based on the beam application. The other project is HZMB tunnel project in Hong Kong. The Hong Kong Zhuhai Macau Bridge HZMB is 5-kilometer bridge tunnel system consisting of the series of 3 cable stage bridge and undersea tunnel and 4 artificial islands. Undersea immersed tube tunnel. The HZMB tunnel is 6.7 km long, of which the immersed section of 5.6 km long is made up to the 33 tunnel element of the switch, 28 straight element and 5 curved elements. This is the public engagement. A series of public engagement achieved enable us to maintain communication with stakeholders on their views and concerns regarding the project. This is the EMA program, Environmental Monitoring and Audit Program. The comprehensive environmental monitoring and audit program is implemented during the construction to the regularly monitored to the environmental impact on various aspects including air quality, noise, water quality, waste management and ecology, etc. This is the integrated beam application. For the progress, the management simulation based on BIM platform is to both optimize the construction process and ensure the actual construction progress by site the supervision of 4D beam model of construction. That is the other project is the deep underground tunnel, Tokyo Outer Ring Road project in Tokyo. This project is the deep underground tunnel, 16.2 km long and 6 lane underground. This is the plan and longitudinal view of Tokyo Outer Ring Road project. This is the typical urban deep underground. As I mentioned, in Japan, introduced the deep tunnel concept. Deep tunnel means 40 meters underground in urban area. Like this. This project is a mega TBM, Japan's largest shield machine. The outer diameter 15.8 meters. Total tunnel length 16.2 kilometers. Like this. All structure is the underground tunnel. This is some in this project the TBM technical issues. Verifying the optimal placement cutter bit can be withstand excavation of long distance as proceed with excavation. We can see the very highly advanced the technology, the TBM technology in this project. This is the CIM, Construction Information Model. CIM is the concept of the principle using the latest ICT technology to share information at each stage, plan, design, execute, and manage to the construction production system in order to build an efficient, high-quality construction the production system in this project. Last project is a Crossrail project in London. The figure shows a project overview. Total the length is the 42 kilometer of under for the Greater London across the urban area using the railway under railway tunnel. This is the project overview. As shown these figures, we can see all the including the underground tunnel, underground the station. This is the tunneling method. Basically the main tunnel using the TBM method, the special tunnel such as the underground station tunnel using some NATM or the SCL tunneling method. This is the beam application in tunneling. You can see some beam modeling in the underground station tunnel. We can see some example of the Liverpool Street station. This is the basic plan view. We can see first of all the existing the survey line and the circle line, the central line, the red color, the London line, and the capital, the connect, and the post office, the railway. Finally, we can modeling the cross line. We can see all the construction stage, the modeling condition. The head of the technical information crossrail, we are creating two railway. The first is the virtual, actual, the construction, the modeling, construction and situation. The second is the digital modeling, using the beam, the modeling, BIM modeling. You can see the twin, the digital, the world. This is the physical railway. The other is the digital railway. You can see the twin, the digital twin simulation in this project. This is the final target for the advanced tunneling technology and the tunneling modeling using BIM, the application, and some urban tunneling underground project. Key issues in mega project, we can review the 5 tunnel project. First is the cable tunnel project in Singapore. The second is the West Connect underway project in Sydney. Third is the HZMB project tunnel project in Hong Kong. The fourth is the Tokyo Outer Ring Road tunnel project in Tokyo. Fifth is the Cross Rail project in tunnel. In this project, we can either summarize the 5 key issues. First is the safety first. The second is the public complaint is a very big issue. The third issue is environmental effect in urban tunneling. The fourth is the mechanized tunneling using the TBM and the load header. Reduce the vibration, noise, and some environmental effect. And the fifth is the digital underground concept using the beam application modeling. And finally, I conclude the combined complex tunneling in the urban tunneling, TBM, load header, the NATM, the SCL is complex and combined for some modern tunneling. A summary and the key words. The mega tunnel project in developed countries. The underground tunnel project in Singapore, Hong Kong, Tokyo, Sydney, London. A continuous effort to address the traffic and the space restriction in urban area. The key issues in the underground tunnel project: increased safety, environment, and the public complaint. And the mechanized construction using TBM and the load header and the beam is more the popular applied. The future task of the underground tunnel construction. Tunnel construction is complex and mechanized construction in NATM or TBM, or the comprehensive and integrated tunnel construction management is applied to the modern tunneling in urban tunneling. This is the reference for this is the presentation. Thank you for your kind attention. I focus on the tunnel risk safety management, especially the urban tunneling. You remember and contact me about some the issues on a problem, tunnel risk and safety management. Thank you. See you later. Bye bye.